Let's discuss Chapter 8, Building the Control Plane, Agent Orchestration in C#. Let's discuss theoretical foundations. The theoretical foundation of cloud-native AI inference rests on the fundamental shift from monolithic, stateful application design to distributed, stateless microservices orchestrated by container runtimes. In the context of autonomous agents and AI inference, this shift is not merely an operational convenience, it is a necessity dictated by the computational intensity, variable load characteristics, and the need for rapid iteration inherent in modern AI workflows. To understand this, we must first establish the core problem: AI inference, particularly with large language models, LLMs, or complex multimodal agents, is computationally expensive. A single request might require seconds of GPU time. If we deploy a monolithic application where the web server, the business logic, and the model inference engine reside in a single process, we face the thundering herd problem. A spike in user traffic immediately saturates the CPU/GPU resources of that single instance, causing queuing, timeouts, and ultimately, service unavailability. Scaling a monolith vertically, adding more power to a single machine, hits physical and financial limits quickly. The analogy: the specialized kitchen versus the diner. Imagine a high-end restaurant, the monolith. The head chef, the inference engine, is a master of a single, complex dish. The waiters, web servers, take orders, the sous chefs prep ingredients, business logic, and the head chef cooks. If 500 customers arrive at once, the kitchen grinds to a halt. The head chef cannot cook 500 dishes simultaneously. You cannot easily hire 100 head chefs to work in the same kitchen, there isn't enough space, and coordinating them would be chaos. Now, imagine a modern food delivery hub, cloud-native microservices. You have specialized stations, a burger station, a sushi station, a salad station. Each station is self-contained, has its own equipment, resources, and can operate independently. If burger orders spike, you don't scale the sushi station, you simply spin up more burger stations. The stations are stateless in the sense that they don't care who ordered the burger, only that they have the ingredients, model weights, to make it. This is the essence of containerized microservices. Let's discuss the containerization of autonomous agents. In C#, we have long relied on the Common Language Runtime, CLR, to abstract away the underlying operating system. However, for AI agents, dependencies are heavy and specific. An agent might require Python libraries for data preprocessing, a specific version of CUDA for GPU acceleration, and a .NET runtime for orchestration logic. Packaging these into a single virtual machine image is slow and inefficient. This is where Docker containers come into play. A container is a standardized unit of software that packages code and all its dependencies, libraries, frameworks, configuration files, so the application runs reliably and quickly from one computing environment to another. In the context of an AI agent built in C#, perhaps using Microsoft.semantic kernel or AutoGen, containerization allows us to encapsulate the agent's decision-making loop alongside its inference dependencies. Why this matters for C# developers: while C# compiles to intermediate language, AI inference often relies on native binaries, like libtorch or CUDA drivers. Containerization ensures that the specific versions of these native dependencies required by your .NET AI libraries are present and isolated. Consider the architectural requirement of an agent that processes natural language and executes code. The agent logic is in C#, but the tokenization might rely on a Rust binary, and the model inference on a Python service. In a monolith, managing these disparate runtimes is a nightmare. In a containerized environment, each component is a distinct image. Theoretical implication: containerization enforces the single responsibility principle at the infrastructure level. A container running a .NET agent should not also be responsible for database management. This separation allows for independent scaling. If the agent's reasoning step is CPU-bound and the inference step is GPU-bound, we can deploy them to different node pools in Kubernetes, optimizing resource utilization. Let's discuss orchestration and the Kubernetes control plane. Once we have broken our monolith into containerized microservices, agent logic, inference service, vector database, cache, we face a new problem: management. How do these services discover each other? How do we handle network traffic? How do we ensure high availability? This is the role of an orchestrator, specifically Kubernetes. Kubernetes acts as the operating system for the data center. It manages the lifecycle of containers, scheduling them onto nodes, machines, based on resource requirements. In C#, we often interact with Kubernetes via the Kubernetes client library. However, the theoretical foundation here is about the desired state. We declare that we want 3 replicas of our inference service, and Kubernetes ensures that if one crashes, it is restarted. If traffic increases, it scales. Referencing previous concepts, in Book 6, we discussed dependency injection, DI, and inversion of control, IOC, in C#. We used interfaces like iInference Provider to decouple our business logic from specific implementations, e.g., OpenAI versus a local model. Kubernetes extends this pattern to the infrastructure level. C#DI decouples code classes at compile time. Kubernetes decouples deployed services at runtime. Just as we inject an iLogger into a constructor, Kubernetes injects network endpoints and environment variables into a pod. We define a service abstraction in Kubernetes, which provides a stable IP address and DNS name for a set of pods. This is analogous to defining an interface in C#. The client, calling service, relies on the abstraction, service DNS, not the concrete implementation, specific pod IP. Moving on to scaling inference, the challenge of statefulness. Scaling AI inference is fundamentally different from scaling a stateless web API. A standard web API, like a CRUD service, is stateless. Any instance can handle any request because the state lives in a database. AI inference, however, often involves loading large models into GPU memory. The cold start problem, loading a 70 billion parameter model into VRAM can take minutes. If we scale from 0 to 10 replicas instantly, the new pods will be cold, they are running, but the model is not loaded. This latency is unacceptable for real-time inference. Strategies for scaling: 1. Horizontal pod autoscaling, HPA. This scales the number of pods based on CPU/memory usage. For AI, this is often insufficient because a GPU might be at 100% utilization during inference but idle between requests. We need smarter metrics. 2. CADA, Kubernetes event-driven autoscaling. CADA scales applications based on the number of events in a queue, e.g., RabbitMQ, Azure Service Bus. In an agent architecture, user requests are often placed into a queue. CADA monitors the queue length. If 1,000 requests pile up, CADA instructs Kubernetes to spin up more inference pods. This is the most effective pattern for AI workloads. 3. Model sharding and parallelism. For very large models that don't fit on a single GPU, we use techniques like tensor parallelism or pipeline parallelism. This requires orchestrator awareness, often via custom Kubernetes operators like the NVIDIA GPU operator. The what-if scenario: what if the inference service is stateful, it holds a conversation context in memory. In traditional microservices, we avoid state in the application layer. For AI agents, we must externalize state. We use a distributed cache, like Redis, or a vector database, like Pinecone or Milvus, to store conversation history. The agent container remains stateless, it retrieves context, reasons, stores the result, and discards the context. This allows any instance to handle any conversation turn. Now, let's explore service mesh, observability and secure communication. As the number of microservices grows, agent A calls inference B, which calls tool C, the network topology becomes complex. This is where a service mesh, like Istio or Linkerd, enters the theoretical landscape. A service mesh provides a dedicated infrastructure layer for handling service-to-service communication. It is usually implemented using sidecar containers, proxies that run alongside our application containers in the same pod. Why is this critical for AI agents? 1. Observability. AI agents are non-deterministic. 2 identical inputs might yield different outputs. We need to trace requests across service boundaries to debug behavior. A service mesh automatically injects tracing headers, e.g., OpenTelemetry, and collects metrics, latency, error rates, without modifying the C# code. 2. Traffic management. We can implement canary deployments. We might want to route 5% of traffic to a new version of our inference model to test its performance. The service mesh handles this routing at the network level. 3. Security. In an agent architecture, one agent might call another external agent via an API. Service mesh enforces mutual TLS, MTLS, ensuring that communication between the planner agent and the execution agent is encrypted and authenticated. Moving on to the role of modern C# in this ecosystem. While the orchestration is language agnostic, C# provides specific features that align perfectly with this architecture. 1. Async enumerability. For streaming inference, AI responses are often streamed token by token to the user to reduce perceived latency. In C#, async enumerability allows us to yield results as they are generated without blocking the thread. This code snippet illustrates a common pattern in cloud-native microservices architectures, specifically how an agent service might interact with an inference microservice to perform real-time streaming inference. Notice at line 1, the comment, theoretical usage in an agent service, which sets the context. This method, stream inference async, is designed to handle a streaming response, which is crucial for applications requiring low latency, continuous updates, such as chatbots or live data analysis. The return type async enumerable string at line 2 is a powerful C# feature for asynchronous iteration, allowing the caller to consume results as they become available without blocking, which is a cornerstone of responsive cloud applications. This design promotes a reactive programming model, where data flows as a stream, enhancing user experience by providing immediate feedback rather than waiting for a complete response. At line 4, we see a wait for each var token in _inference client.getStreamAsync prompt. This is where the magic of asynchronous streaming happens. The _inference client is an abstraction representing our connection to the actual inference microservice. Its getStreamAsync method is expected to return an async enumerable string itself, which means it's also designed for streaming. The wait for each construct then allows us to iterate over the incoming tokens from the inference service as they arrive, without blocking the calling thread. For every token received, yield return token, at line 7 immediately sends that token back to the caller of stream inference async. This yield mechanism is fundamental to async enumerable, enabling the producer, the inference service, and consumer, the agent service, to work in a pipeline fashion. This approach significantly reduces end-to-end latency and memory footprint, as we don't need to buffer the entire response before sending it, which is crucial for handling large AI model outputs in a resource-constrained containerized environment. This is crucial for HTTP/2 streaming responses in Kubernetes, where keeping connections open is efficient but blocking threads is costly. 2. System, threading, channels for backpressure. When scaling microservices, we must handle backpressure. If the inference service is overwhelmed, the agent service shouldn't crash. Channels provide a producer/consumer pattern that integrates with the async pipeline, allowing us to buffer requests gracefully before they hit the queue. 3. Source generators for performance. In high-throughput inference scenarios, JSON serialization can be a bottleneck. Modern C# source generators allow us to generate highly optimized JSON parsers at compile time, using system, text, JSON, reducing the CPU overhead of marshalling data between microservices. 4. Records and immutability. AI agent workflows are complex state machines. Passing mutable state between services is dangerous. C# records provide immutability by default. Here, we're defining a C# record named agent context. Records are a relatively new feature in C#, introduced in C number 9, that are particularly well suited for immutable data models. They automatically generate methods like equals, getHashCode, and toString, which is incredibly convenient for data transfer objects, DTOs, or, in this case, a context object that encapsulates the state of an agent's interaction. This immutability is a key principle in functional programming in cloud-native development, as it simplifies reasoning about state changes and helps prevent unexpected side effects, especially in concurrent or distributed systems. When we pass this context around, we know its internal state won't be modified unexpectedly by different parts of our application. Using records ensures that when we pass context from the agent service to the inference service, we are passing a snapshot in time, preventing race conditions in distributed environments. Moving on to theoretical foundations. The transition to cloud-native AI inference is driven by the need to isolate heavy, specialized workloads and scale them independently. We achieve this by 1. Containerizing the agent logic and inference engines to ensure environment consistency. 2. Orchestrating these containers using Kubernetes to manage lifecycle and placement. 3. Decoupling state from computation, using external stores, vector DBs, to maintain conversation context. 4. Scaling based on events, CADA, rather than just CPU metrics to handle the bursty nature of AI workloads. 5. Observing the distributed system via a service mesh to manage the complexity of inter-agent communication. This architecture transforms AI inference from a fragile, monolithic bottleneck into a resilient, scalable, and observable system capable of supporting complex autonomous agents. Moving on to basic code example. Here is a basic code example demonstrating how to containerize a simple AI inference microservice using C# and ASP.NET Core. We start by importing necessary namespaces. These using statements at lines 1 to 7 bring in core ASP.NET Core framework components. Specifically, Microsoft.ASP.NET Core Builder, Microsoft.ASP.NET Core Hosting, and Microsoft.ASP.NET Core HTTP are fundamental for building web applications, defining the request pipeline, and handling HTTP contexts. Microsoft Extensions. Dependency injection is crucial for configuring the application services, while Microsoft Extensions hosting provides infrastructure for host management. Finally, System Text JSON and System Text JSON serialization are included for efficient JSON serialization and deserialization, which is a common requirement for API communication, especially in cloud-native microservices. At line 10, we declare the AI inference service namespace. This acts as a logical container for all related classes, helping to organize the codebase and prevent naming conflicts, which is good practice for larger projects and microservices architecture. The program class, line 60, is the entry point for our application, following the standard structure for ASP.NET Core applications. Here, at lines 13 to 21, we define inference request, a data transfer object, DTO. This DTO is critical for defining the contract of our API. It explicitly outlines the structure of the JSON payload that our AI service expects from clients. Notice that JSON property name, prompt, attribute at line 16 and JSON property name, max_tokens, at line 19. These attributes from system, text, JSON, serialization allow us to map JSON property names, which are typically snake_case in web APIs, to C# property names, which are Pascal case, ensuring clear communication between the client and our service. This separation of concerns, defining clear input structures, is a hallmark of robust API design and microservices. Similarly, at lines 23 to 32, inference response is another DTO, but this one defines the structure of the data our AI service will send back to the client. It includes a result, line 28, to hold the AI's generated output and model version, line 31, which is a useful piece of metadata for clients to understand which version of the model processed their request. This is particularly important in cloud-native environments where multiple versions of a service might be running simultaneously, e.g., B testing, canary deployments. Providing this version information helps in debugging and ensures clients know what to expect. Like inference request, it uses JSON property name for clear JSON mapping. At lines 34 to 40, we introduce the inference service interface. This is a crucial architectural decision. By defining an interface, we decouple the AI's core logic from its implementation. This promotes the dependency inversion principle, making our system more flexible and testable. In a real-world scenario, this interface might be implemented by a class that interacts with a complex machine learning model, e.g., an ONNX runtime, TensorFlow serving, or a cloud AI API. For our current example, it allows us to easily swap out a mock implementation for a real one without changing the consuming code, like our API endpoint. This separation is vital for microservices, enabling independent development and deployment of the AI logic. Here, at lines 42 to 57, we have mock inference service, which is a concrete implementation of our inference service interface. This mock service is incredibly valuable for development and testing. At line 47, await task, delay, 100, simulates processing time or network latency, which is essential for understanding how a real AI model might behave under load. Without this, performance characteristics might be misrepresented. The result at line 51 provides a basic, deterministic response. This mock allows us to build and test the API endpoint and client-side integration before a complex, resource-intensive AI model is fully integrated, accelerating development. It also helps to keep our container images small during development by not requiring the actual heavy AI model. At lines 59 to 66, we find the program class, which is the standard entry point for an ASP.NET Core application. The main method is where our application's execution begins. Web application.createBuilder, args, at line 65 is the starting point for configuring our web application. It sets up a host with default settings, including Kestrel, the default web server, logging, and configuration sources. This builder pattern allows us to fluently configure services and the request pipeline, which is a clean and extensible way to bootstrap an application. Notice at lines 67 to 70, we register our mock inference service with the dependency injection, DI, container. Builder, services.add singleton inference service, mock inference service, is a critical line. We register inference service to be implemented by mock inference service as a singleton. This means only one instance of mock inference service will be created throughout the application's lifetime and shared across all requests. For real AI models, this is a common and important pattern because loading a large model into memory is often a very expensive operation. We want to do it once and reuse that single instance to save memory and startup time. If we were to create a new instance per request, e.g., add scoped or add transient, the memory footprint and load times would be prohibitive, especially in a containerized environment where memory is a precious resource. At lines 72 to 75, var app equals builder, build, finalizes the application's configuration, creating the web application instance. Following this, app map post/inference defines our API endpoint. This uses ASP.NET Core's minimal APIs feature, which allows for concise endpoint definitions without the overhead of controllers. We're mapping a post request to the /inference path. This is conventional for operations that create or process data, like submitting a prompt for AI inference. The Lambda expression defines the handler for this endpoint, taking HTTP context and our inference service as parameters, which are automatically provided by the DI container. Within the map post handler, at lines 76 to 85, we handle the incoming request. Await context, request.read from JSON async inference request, at line 78 deserializes the JSON body of the HTTP request directly into our inference request DTO. This is very efficient and leverages the system, text, JSON capabilities. Lines 80 to 84 perform basic input validation. If the request is null or the prompt is empty, we return a 400 bad request status code with an informative message. This early validation is a best practice to prevent unnecessary processing and provide clear feedback to clients, which is crucial for building robust microservices. Finally, at lines 86 to 92, we execute the core logic and return the response. var response equals await inference service.generate async request. At line 88 calls our injected inference service to perform the simulated AI inference. Because inference service is injected, we don't care if it's the mock or a real model, the code remains the same, demonstrating the power of dependency injection. Await context, response.write as JSON async response. At line 91 serializes our inference response DTO back into JSON and writes it to the HTTP response. This completes the request response cycle, delivering the AI's output back to the client. This entire endpoint is stateless, meaning it doesn't store any client-specific information between requests, which is a key characteristic for horizontal scalability in cloud-native applications. The last step in our main method, at lines 94 to 97, is app run. This command starts the Kestrel web server, making our application listen for incoming HTTP requests. Kestrel is a fast, cross-platform HTTP server that is optimized for ASP.NET Core. Once app run is called, the application will continue to run until it's explicitly stopped, processing requests as they come in. In a containerized environment, this is the command that keeps the container alive and serving traffic. Let's discuss Dockerfile for containerization. To deploy this microservice, we need a Dockerfile. This file defines the environment and builds the application into a runnable container image. Alright class, let's start by looking at lines 1 to 3. Here, we're defining the first stage of our multi-stage Dockerfile, named build. We're pulling the mcr.microsoft.com/.net/SDK 8.0 image. This is crucial because it provides the full .NET SDK, which includes compilers, runtime, and all necessary tools to build our application. We then set the working directory inside the container to /src. This build stage is designed to be self-contained and will produce the compiled artifacts, separating the build environment from the runtime environment. This is a best practice in containerization, as it leads to smaller, more secure final images. Moving on to lines 5 to 7, we're copying just the AI inference service.xproj file into our /src directory. Immediately after, we run .NET restore. This command downloads all the NuGet package dependencies specified in our project file. By copying only the .xproj file first and restoring, Docker can cache this layer. If only the source code changes, but not the dependencies, Docker won't rerun .NET restore, significantly speeding up subsequent builds. This is a critical optimization for continuous integration pipelines and developer iteration times. At lines 9 to 10, we copy the rest of our application's source code into the /src directory. This happens after the .NET restore step. If we had copied all files at once before restoring, any change in the source code would invalidate the cache for the .NET restore layer, forcing a full restore every time. By separating these steps, we leverage Docker's layer caching effectively, ensuring that only necessary layers are rebuilt when changes occur. Now, at lines 12 to 13, we execute .NET publish c release o/app/publish. This command compiles our application, resolves all dependencies, and publishes the output to the /app/publish directory. The C release flag ensures that the application is built in release mode, which typically includes optimizations and excludes debugging symbols, resulting in a smaller and faster executable. The o/app/publish specifies the output directory for the published artifacts. This publish step creates a self-contained application that can be run on any machine with the .NET runtime, without needing the SDK. Let's look at lines 15 to 17. Here, we initiate the second stage of our multi-stage build, named runtime. We're using the mcr.microsoft.com/.net/aspnet 8.0 image. This is a much smaller image compared to the SDK image, as it only contains the .NET runtime necessary to execute ASP.NET Core applications, not the build tools. This choice directly contributes to the principle of creating lean, production-ready container images. We then set the working directory to /app, which will be the root for our deployed application within the final container. At lines 19 to 20, we use copy from equals build/app/publish. This is the core of the multi-stage build pattern. We are copying only the published output from the build stages /app/publish directory into the runtime stage's current working directory, /app. This is a critical step for reducing the final image size. We discard all the build tools, source code, and intermediate artifacts that were part of the build stage, resulting in a significantly smaller and more secure production image. This directly supports cloud-native principles of efficiency and minimal attack surface. Now, at lines 22 to 23, we have expose 80. This instruction informs Docker that the container listens on port 80 at runtime. While expose doesn't actually publish the port, you'd use p with Docker run for that, it serves as documentation for the user and can be used by other tools, like Docker run, publish all. For an ASP.NET Core application, port 80 is the default HTTP port. This is essential for allowing external traffic to reach our inference service once it's deployed, for example, within a Kubernetes cluster or directly on a host. Finally, at lines 25 to 26, we define the entry.net AI inference service.dll. This specifies the command that will be executed when the container starts. It tells the container to run our published application using the .NET command. The AI inference service.dll is the compiled entry point of our ASP.NET Core application. This ensures that when the container is launched, our AI inference service automatically starts up, ready to serve requests. Using entry.net over CMD is often preferred for executables, as it makes the container behave like an executable itself, and CMD can then be used for default arguments to the entry point. Thank you for your attention. This lesson is excerpted from Volume 7, Chapter 8 of the C# and AI Masterclass ebook series and from the volume Cloud Native AI and Microservices, Containerizing Agents and Scaling Inference. You can find all the details here. https://github.com/edgarmilvas/C# programming series. The ebook also includes diagrams, advanced examples, and 5 exercises with solutions for every chapter. There are 26 chapters. If printed, it would exceed 600 pages. Subscribe to the channel to watch more videos. I look forward to seeing you in the next lesson.